everyone, hope you have a pleasant day. My name is Ghasemi, a faculty member of the Agricultural Biotechnology Research Institute of Iran. My research interests include plasmonic and luminescent nanoparticles, the design of colorimetric and colorimetric sensors, and development of sensor arrays for medicinal, agricultural, and environmental purposes. In this presentation, I aim to introduce the principles and application of nanoplasmonic sensor arrays. I have to turn off my camera, otherwise it will cover a part of my slides.
Nanoplasmonic sensor arrays. As in many other methods that have integrated nanoparticles, the chemical sensor array strategy have also progressed greatly since the entrance of nanoparticles into this field. The fascinating tunable physicochemical properties of nanoparticles have made them powerful candidates for array-based sensing platforms and have enabled the development of real-time and sensitive systems that are able to detect a target analyte. In particular, the unique optical properties of plasmonic nanoparticles, especially gold and silver, have a key role in providing promising array-based sensing approaches. In this presentation, I will describe fundamental steps in the design of nanoparticle-based sensor arrays, along with some examples of my works.
It was a belief that the tongue consists of five regions, each containing specific receptors for a taste: sweet, salty, sour, and bitter. Due to the variety of existing tastes as well as encountering new tastes, the taste system certainly does not have specific receptors for each smell and taste. This type of molecular detection can't be based on the usual model of specific interactions, such as the lock and key mechanism. Therefore, the initial belief can't be correct. In the new model, the taste receptors scatter through the tongue. The gustatory system consists of semi-selective receptors. Each one produces a response to a taste, and the pattern created by the response of all receptors is a specific receptor to each taste. As a result, the response to a limited number of semi-selective detectors creates a large library containing a variety of flavors. In the last few decades, many advances have been made in modeling the olfactory and gustatory system and the design of noses and electronic tongues, which I mean sensor arrays. We are talking about them in the next slides. Sensors can be classified into two categories in terms of recognition elements: the ones with specific recognition elements and the one with cross-reactive recognition elements. In the first category, a highly selective probe is designed to respond to one particular analyte. The scheme here illustrates three lock and key sensors in which each sensor specifically interacts with only one analyte. You see the purple sensor only interacts with this triangle analyte. Therefore, the response is only for this triangle analyte. For all of them, we see there is only one specific response for only one analyte. Though sensitive and specific, these ideal sensors usually require expensive sensing units such as enzymes, antibodies, aptamers. Moreover, time-consuming synthesis processes might be needed to achieve such specific sensors. In the second category, more than one analyte can be detected and identified by using a group of cross-reactive recognition elements arranged in an array format, which is called a sensor array. For example, here these three sensor elements are a sensor array. All of them are a sensor array. This scheme illustrates a sensor array in which three cross-reactive sensors interact with several analytes and produce a distinctive pattern for each analyte. Here there is a pattern for this cube analyte, and here there is a pattern for triangle analyte. The sensor array mimics the mammalian gustatory and olfactory principle, in which all responses collected from non-specific receptors represent a fingerprint-like pattern for each taste. Designing a number of sensing elements with different binding affinities towards different analytes is the first step in array-based sensing. These are our sensing elements with cross-reactive interaction with different analytes. There are a positive correlation between the binding affinity of the recognition element and the analyte. The stronger interaction between the sensing element and the target results in higher signal, and the weak interaction results in a low response signal. In the second step, the response profiles of each analyte upon its interaction with sensing element are recorded. In the array strategy, the response signal from all sensing elements are collected for each analyte. Here you see three signal from sensing element 1 for three analytes. Um, uh, Therefore, rather than focusing on individual response signal, which result in a fingerprint-like analyte response. Depending on the number of sensing elements, a multivariate data matrix is obtained, which is then analyzed and processed by a suitable pattern recognition method. Discrimination among different analytes and also prediction of the identity of unknown analytes are the main objectives of this whole procedure. Pattern recognition methods are well-established chemometrics tools which are used to classify, identify, and quantify the target analytes. There are generally two types of pattern recognition methods: supervised and unsupervised method. In the supervised methods, based on the response signals of known samples, the distinct patterns in the data are recognized and subsequently used for the identification of unknown samples. In contrast, in unsupervised pattern recognition methods, in which a data based on known sample has not been previously created, the aim is to just discriminate among samples, not to recognize the sample itself. Apart from visual interpretation of the results of pattern recognition based on the score plots and dendrograms, the raw data collected from the sensor elements can also be visually assessed by different graphs based on meaningful differences in colors or graphical patterns. Heat maps, bar plots, and color difference maps are among common data visualization methods which are used to visually display the numerical response profile profile collected from the sensor arrays. The resulting graphical and colorful representations facilitate the interpretation of the result and allow visual evaluation of arrays' performance in discriminating the classes of analyte. Among numerous chemical compounds, such as different kind of dyes, chemoresponsive dyes, Lewis acid-base dyes, Bronsted acidic or basic dyes, redox indicator dyes, molecularly imprinted optical sensors used as sensing elements, the emergence of nanoparticles can be considered a milestone in the sensor element design. In the case of colorimetric sensor arrays, fascinating surface properties, ease of surface modification, good stability, tunable physicochemical properties, and size and environmental dependent optical properties make plasmonic nanoparticles powerful candidates in array-based sensing performance. Plasmonic nanoparticles, mainly gold and silver nanoparticles, exhibit a unique and tunable photophysical features on account of their surface plasmon resonance (SPR). The SPR properties of plasmonic nanoparticles are originate from the collective coherent oscillation of the conduction band electrons when they are in resonance with the incident electromagnetic radiation. The SPR properties of plasmonic nanoparticles depends on the composition, size, shape, surface coating, and dielectric constant of the nanoparticles and surrounding medium, and have led to their wide application as efficient and versatile platforms in optical sensors. Colorimetric sensing strategies using plasmonic nanoparticles are usually based on the change of optical properties of nanoparticles due to their aggregation, anti-aggregation, or growth of nanoparticles, which result in visible color transformation of plasmonic nanoparticles. In the next slides, I will present the application of plasmonic-based sensor arrays into three categories: aggregation, anti-aggregation, and growth of nanoparticles. The optical properties of plasmonic nanoparticles depend strongly on the interparticle distance between pairs of nanoparticles. A decrease in interparticle distance induces surface plasmon coupling of nearby particles, causing a redshift in the SPR band and a visible color change from red to blue for gold nanoparticles and a yellow to brown color alteration for silver nanoparticles. The color change during gold or silver nanoparticle aggregation provides a vast number of applications for colorimetric sensing of any target analyte that may directly or indirectly lead to gold or silver nanoparticle aggregation. For example, we use the aggregation mechanism to develop a nanoparticle-based colorimetric sensor arrays by utilizing label-free gold and silver nanoparticles for visual detection of beta-amyloid peptides 42 and 40, and also human serum albumin. Different aggregation behavior of nanoparticles through the conjugation of nanoparticles with beta-amyloid peptides and then coordination of beta-amyloid peptides peptides with copper ion lead to diverse spectral and color changes. Here you see the different spectra. For example, the red one is for blank of gold nanoparticles. The green is for human serum albumin. The blue one is for amyloid beta 14, and the yellow is for amyloid beta 42. Therefore, we have two patterns, one of them from gold nanoparticles and another from silver nanoparticles. Here you see the color of our probe. We have two responses for each analyte. Blank is red, and this color for gold nanoparticles and silver nanoparticles. The pattern for amyloid beta 14 is completely different with human serum albumin or amyloid beta 42. TEM, transmission electron microscopy images, confirm that beta amyloid peptides cause the aggregation of nanoparticles. This image is the TM image of gold nanoparticles. Then we add amyloid beta 14. Nanoparticles are getting aggregated. This one is for amyloid beta 42. This image shows the silver nanoparticles, and then we add amyloid beta 40 and amyloid beta 42. These images prove that the nanoparticles are aggregated because of the presence of amyloid beta and also copper ion. Heat map, a two-dimensional representation of numerical results, was employed to visualize the unique response of pattern of each analyte. We have a unique pattern for amyloid beta 14. We have another unique pattern for amyloid beta 42 and a unique pattern for human serum albumin. According to the bar plots and the heat maps, one can easily differentiate structurally similar amyloid beta peptides without the need for any statistical techniques. Quantitative discrimination among amyloid betas and human serum albumin was obtained using linear discriminant analysis. The proposed sensor was able to discriminate among amyloid beta peptides and human serum albumin in different concentration of 50 to 500 nanomolar. In the anti-aggregation strategy, an analyte with higher affinity than aggregation reagent inhibits the aggregation of nanoparticles or disperses the aggregated nanoparticles. So in this mechanism, first we have aggregated nanoparticles, and then with adding the analyte, it causes the dispersion of nanoparticles. Our group presented the first report of anti-aggregation based sensor arrays. The strategy is based on the competitive interaction of citrate-capped gold nanoparticle and heavy metal ions with three aggregation reagents, cysteine, arginine, and melamine. In the presence of aggregation reagent, the color and UV visible spectra of gold nanoparticles are changed, indicating the aggregation of gold nanoparticles. Addition of aggregation reagents, which are firstly treated with the ions, causes gold nanoparticles turn from aggregation to dispersion states. The anti-aggregation capability of ions toward various aggregation reagents is different because because of distinct stability constants of ion aggregation reagent complexes. Here you see the pattern from the first sensor element, second sensor element, and third sensor element, and their colors. The first row is the pattern of blank, the second mercury and other ions. The combinatorial colorimetric response of all sensor elements enables discrimination among the ions with various concentration by LDA or linear discriminant analysis. You see, the ions in a wide range of concentration are classified in different groups. The third mechanism that I want to explain to you, growth. Overgrowth of gold nanoparticles and silver nanoparticles happens through the reduction of silver or gold ions on the surface of nanoparticles. The deposition of silver or gold shell may direct the changes in the composition, size, shape, refractive index of nanoparticles, and consequently the variation in the SPR band and color of nanoparticle solution. As an example of growth mechanism, we designed a multicolor sensor array consisting of two types of gold nanostructure: gold nanorods and gold nanospheres, for discrimination and determination of critical biogenic amines. Here are 6 biogenic amine: spermine, tryptamine, ethylenediamine, tyramine, spermidine, and histamine. The design principle of the probe was based on the metallization of silver ions on the surface of gold nanorods and gold nanospheres in the presence of biogenic amine. Here you see in the blank we have an gold nanorod. When the silver shells on the surface of gold nanorods, you see it, we have both changes in the color of solution and the spectra of nanorods, and also for gold nanospheres. Changes in the surface composition, size, and aspect ratio of gold nanorods and gold nanospheres induced a blue shift in the plasmonic band, which was accompanied by sharp and rainbow-like color variation in the solution. The shape of gold nanorods changed to dumbbell-like, aligned with a decrease in the aspect ratio from 4.2 to 2.8. Here gold nanoparticles in blank, and then the silver shell on the surface of gold nanorods. And also the size of gold nanospheres changed from 25 nanometers to 13 nanometers. Here you see clearly a shell of silver on the surface of gold nanorods. Applying linear discriminant analysis, the proposed colorimetric sensor array accurately distinguished among the analyte in a wide range of concentration. Each analyte in a wide range of concentration are grouped without any error. Finally, the practical applicability of the sensor array was investigated by the determination of biogenic amines in meat sample. Here you see we spiked spermidine, and it was identified correctly in its group, or also for tryptamine, which we have shown them with lighter color. attention. If you have any question, I will be happy to answer them now in this session or later through my email.